Hello, I'd like to introduce our LEAM electron beam gun with automatic beam changer and cation deflection coil. Built for 80 to 150 kV additive manufacturing and welding applications. My name is Ralph Edinger. I'm from Camorra Tech Inc., British Columbia, Canada. Today's production requires more than a single tool to manufacture parts. Machines without a tool changer are not able to make the product. Therefore, state-of-the-art CNC machines have automatic tool changers, ATC. These ATCs allow the automatic change of tools in a production cycle. Today's electron beam machines have a single beam assembly, cathode-anode, and have only limited process adaptability. Our new LEAM electron gun incorporates a number of new innovations, one being the automatic beam changer, ABC, which allows to change bias, cathode, and anode automatically under vacuum during a process. The upper beam column includes an ABC drive, high voltage isolator, bias section, cathode section, anode section, coil, and stigmata coil. Upper column and lower column are separated by a gun vacuum valve, which means that we can have different vacuum pressures during the process cycle. The lower beam column includes a optical system that allows the attachment of visible or infrared cameras, a focus coil, and a cation deflection coil. Let's see how this works. The drive, which is usually a stepper motor, can rotate a carousel assembly, and in the carousel assembly you will find the cathodes, up to 5. Below the bias and cathode assembly is the anode carousel, which holds the corresponding anode shape for a specific cathode. This means that up to 5, in this case, different cathodes can be used with different beam parameters. In addition to that, you could choose to have sister cathodes. For example, if there is a very long production cycle, you could have 2 of the same cathodes, and after a certain amount of time, you can change to a new cathode. This shows the anode assembly. On top of that, we developed the multi-column technology. This allows us to produce a multi-beam, which is a real multi-beam, having multiple beam columns, in this case 4 independently controllable beam systems that are linked together in a housing. For example, on a 4-column system, you have 4 times 200 by 200 millimeter melting area, so that will total an area of 200 by 800 millimeter, which can be produced at very high speeds. A 3-gun column system would have an area of 200 by 600 millimeter. We would like to introduce our cation deflection coil, which is really focusing on the control of the beam position on the surface of the product. Typical deflection coils in use today have a magnetic error causing the beam having to position in various unknown areas, which means if I send a current to an X coil, actually the beam moves in X and Y. Our system is developed in order to overcome this problem. That means the current goes in an X coil, only moves the beam in X direction, not in Y. Therefore, the beam position is very predictable. On top of that, it is designed to run up to 10 kHz deflection frequencies. This allows us now to develop different melt strategies. What do we mean with this? The traditional way is that the shape of the part basically gives you the trajectory or the positioning of the beam over the product, which is traditional geometric melt pool. The form of the melt pool, top bead, under bead, and the taper of the weld is pretty much limited based on maybe some deflection patterns, some different tricks we can do with the beam in order to optimize these melting behavior. Now the new system we developed is called time domain. The time domain means that we still have to run the beam similar to the beam shape, but we are separating this by different timings. So we divide the melt pool in time zones, and these time zones are open programmable. That allows us to actually shape the melt pool better. What does this mean? That we can actually control the top and bottom beam much better, as well we can control the melt pool taper. This could be interesting for welding and additive manufacturing processes. Let's have a look how that looks like from a modeling perspective in the melt pool. So the gray area is the melt pool. Here, a conventional way where we actually move the beam across a weld line. On the right hand side, you see the melt pool formation where we switch the beam on for 5 milliseconds and off for 50 milliseconds and move the beam in this time frame forward and back. As you can see, the temperature development is very different. The melt pool depth, the gray area, is almost similar, which means that we can weld parts at different time temperature profiles. And that allows us to make complete new processing. Let's have a look at the different timing. So we use both simulations show time domain melting, but one is 5 milliseconds beam on, the other one is 50 milliseconds beam on. So as you can see, the cooldown, the temperature development in the part is very different. And this is completely programmable and open source control. So let's have a look at a real application in a camera view. So on the left hand side, this is geometric domain. So these lines would correspond the actual part shape. This is just an example. Now, we in the time domain, as described, we have actually two melt pool formations, one being discrete melt pools and linked melt pools. So let's look at the discrete melt pools. So the beam is moving so fast between each position that you can generate 4 or multiple independently melting points. This is a different strategy for certain processes. The linked melt pool means we do the same thing in a discrete, but the movement between two melt lines is so close that the actual melt pool is still linked. And that allows us to actually create parallel melt pools. This is interesting for certain welding and additive manufacturing applications. All of this is actually programmed in G-code. So that was another work we had to develop a control system that is fast enough that allows us to have an open source system where we can flexibly program the timing of each beam and have trajectories generated that are fast enough. So this is done with an Omron delta tau control system, which we have developed a different operating system, and the user interface is shown here on this side. So all open source, you can see G-code as any machine, and programming can be done in two ways. One is our slicer for complex applications. Another way could be as simple as an Excel file where you program the code required, you calculate the positions, and then you export the file as an ASCII file and import it in the control. Very simple. So summarizing, we have a new electron beam gun technology that allows up to 5 beam stations, which can be automatically changed. So you can create own cathodes, you can run them, and you can switch them in a process. Real multi-beam with any number of beam columns is possible for extreme increase in productivity. As you can see, you can run beams at the same time without losing time. High-speed Cartesian deflection coil allows us traditionally operation and new time domain processing. So we would like to really emphasize on that a calibration before that is not required because we know where the beam will go. All this technology is available in either one of our LEAM-1, 4, and 8 systems. So we can provide you with a machine that incorporates these technologies. I would like to thank you for listening, and for more information, please contact me. Thank you. Bye-bye.